This is video 13 exploring serial transfers on STM32 MicroPython and a desktop Python application. The code for this video is at the GitHub site. The information presented in these videos on MicroPython should work as well on any STM32 F4 board. All code examples have pin definitions at the beginning of the file to allow the programmer to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like as that really helps. In this video, we use the STM32 F411 baseboard with an external Bluetooth UART module to exchange data with a desktop Python application. The benefit of this study is to discover a better approach to data exchange between systems, that is, all Python. It avoids exposing our data to the internet and so provides an alternate to network connections, though I will be using wireless Bluetooth devices. Finally, I want to find, build, and reuse code that can be integrated with future solutions. Begin by searching the internet to see if there is a proper way to perform serial transfers. During the searches, we find the OS model explains network transfers. It has terms like frames and packets. A search, simple serial point-to-point communication, finds a post at Stack Overflow that discusses serial transfers using frames and casually mentions several software products. I found an old blog post, Framing in Serial Communications, by Eli Bendersky that is important to our exploring, as it explains a frame in great detail and the need for start byte and escape bytes. Another old blog post, SLIP, in other words, Serial Line Internet Protocol, by Asanka Sayakara, in which he took an old internet protocol and converted it to Python. In yet another search, Serial Communication, Unique Start of a Serial Packet, discusses a way to build the frame using a different escape byte approach called COBS, in other words, Consistent Overhead Byte Stuffing. The discussions on frames also raise concerns that the code handles arriving bytes continuously. For example, if a microcontroller is restarted, it needs to ignore arriving bytes until it finds the start of a new frame. It needs to treat subsequent start bytes via an escape byte. All of the approaches discussed checksums, or CRCs, that is, cyclic redundancy check, as a means to detect errors and reject the frame or packet. My search located 8-bit, 16-bit, and 32-bit CRCs, which are 1, 2, or 4 bytes respectively. Interestingly, I found that several software products use the 2-byte CRC16 checksum. Enough research. Let's build our system and a simple program to understand the concepts. Here, the microcontroller platform is our STM32 baseboard with a Bluetooth UART module. Either a BLE or a classic Bluetooth board will work. For my testing, the Bluetooth classic board was the easiest to start with. In either case, the Bluetooth module is simply inserted into the female header of the Bluetooth UART board. Then we can use the Bluetooth feature on our desktop to wirelessly connect. On STM32 side, our UART connects to the Bluetooth module, and on the desktop side, we will use Pi serial connecting to the desktop Bluetooth. Initially, we will simplify the hardware by wiring our UART in a loopback. We do that by temporarily removing the Bluetooth module and place a DuPont wire that connects the TX pin to the RX pin. Let's look at the code. I have up a similar copy to the routine we used in video 4. It's a Thony routine. Let's run it. You can see that the program is initiated by using the user button to start the send of the data. Here's the write statement that's invoked when I press the button. And here's the read in time. In case any data is arriving, it will be read by this routine and then printed byte by byte. Let's run it. You can see I sent the message hello, which is 5 bytes, and it was read byte by byte by the UART-any routine. Okay, we want to use that same concept in another version of the program that uses framing. Let's add framing to this basic program. A frame is a start byte, the payload size, multiple bytes for the payload, an 8-bit checksum, and an end byte. Here I've defined the special byte characters. The start byte is a 7E, the end byte is a 7D, and the escape byte is a 7C. The idea here is to show the various stages to build the frame from our message as well as parse the received bytes. Let's click the green run icon to execute the program again. Okay, and press the user button. Here we've sent the message hello again. It's 5 bytes. We built the frame using the escape characters that I mentioned earlier. It's now 9 bytes. Then we use the byte stuffing routine to escape any characters that might be in the frame. And we found one and added a byte. And then we transmit it. Now this frame is then received by the loopback and printed out 1 byte at a time, just like in the loopback example we did earlier. As it does that, we use a finite state machine to parse through these bytes to arrive at our message. Let's look at the code in more detail in the same order. First, we'll look at the send routine. It's the build frame routine in which we want to build the frame using a start byte, a size byte, multiple bytes for the message, a byte for the checksum, and a byte for the end character. You can see in this routine, we start with the buffer 0 and we insert a start byte. Next, in buffer 1, we add the size of the message. In bytes 2 through whatever, we insert the bytes for the message. Now we extend the buffer with 1 byte for the checksum, and we extend it again with 1 byte for the end byte. And then we return this buffer to the main program. As you recall, the next step is to stuff it. So we have a byte stuff routine. The byte stuff routine reads through the frame message byte by byte, and it's looking for the start byte, end byte, or escape byte inside the frame. And if it finds it, it inserts an escape byte, increases the count by 1, extends the buffer, and then it adds the byte that was originally in the frame. If it doesn't find it, it just adds the character byte that it found in the frame. When it's done, it calculates the size and sends the buffer back to the main program. And so in this case, it looked through this stream, and as you can see, using this count greater than 0, we have a special case for the start byte. But the end byte it finds, and so it inserts this escape character inside, and that's why the buffer went from 9 bytes to 10. And that's what's transmitted. These 10 bytes are transmitted to the other system. In this case, since we're using loopback, it's sent to ourselves. And we use the receive routine to parse the data. The receive routine is using these states for the finite state machine to parse the data. And it begins with the current state, as you can see in this reset of locate the start. All right, so let's go down to the receive routine. And we work backwards. So at the very bottom of our routine, we look to see if we find a start byte. If we do, and the last byte was none, which it would be because it's the first byte, then the current state is set to locate the size because we now have the start byte. We don't need it for anything else, so we just throw it away. Remember, this is a pass-through, so it's receiving bytes, and unless we store them, it's just passing through the routine. All right, the next byte comes in. So that was the 7E byte. Okay, the next byte that comes in is the 05, which is the size byte. And our state machine is saying that we're waiting for, waiting to locate the size. So since that's the statement that we're looking for, here it is, find the payload size. So if the current state is locate size, which it is, it sets the payload size variable equal to the byte that we just received. And since that's all we need, we now set the current state to locate the payload. Okay, it circles back around and gets the 68, which turns out to be an H. And it comes into the routine. It finds this part of the code where the where it's looking for the current state is equal to locate payload. Because of that, it takes the byte value and puts it into a new buffer called indata, and it sends the last byte to that value as well. Then it increments the counter for this indata buffer. If the in count for this buffer is equal to the payload size, then we will exit this routine and change the state. However, since we are expecting 5 bytes, it's not reached that point yet. So it drops through and we read another character, in this case, the character 65, which is the E character. So that gets put into the indata buffer and all the pointers are incremented. Then the 6C is read. The next 6C is read. The 6F is read, and it's the 5th character. So now the in count is equal to the payload size, and our current state is now set to locate checksum. All right, so here's locate checksum. The code drops through, and it receives the next byte, which is a 77. And the code finds that it's looking for a current state of locate checksum. Since that's the state that we're in, it sets this whole checksum variable equal to that byte. And now it says locate the end. And so it drops through and reads the next character. Well, the next character is a 7C, and as you recall, 7C is our escape character. So we look for that at the beginning of the routine. So at the beginning of this routine of where we're receiving bytes, we are looking at each input, at each incoming data value, and looking to see if it's equal to our escape byte. Okay, if it's equal to the escape byte and the last byte was also escape byte, then we handle that. In this case, the last byte was not an escape byte. As you recall, it was the letter O. So it reaches this point. So here it says, oh, I've performed an escape. Okay, so I'm going to set the last byte equal to escape byte and return immediately, not save it or anything. Just drop out of the code, return, and get another character. So it's going to ignore this escape. And that's good. So the next character it receives is the 7D. Well, when the code comes through, it's not an escape character, so it doesn't hit anything at the top. It comes all the way through all these routines, and it says if the data is equal to n byte and the last byte is equal to none, then process it. So now it takes and trims the data that we got from the payload. It calculates a checksum, and it compares this checksum with the value that it just read in, the byte value that it just read in earlier as the checksum. And if they're equal, then it sends the response. If not, it prints out an error message and returns nothing. And as a result, we have the 5 characters in the indata buffer, and that's what is passed right here to our response. Okay, and so if the response is not none, then we receive the data. And here you see we receive the data. Okay, let's make sure that the escape character is working. Let's go modify our message. So on line 193, we've defined our message as hello. We can comment that out and use this other message. In this other message, I build the message with our escape characters. Here I've inserted an end byte, and at the end I've inserted an escape character. So that we want to see that in our payload when it finishes. So we'll have HE, this end byte character, LLO, and the escape character. And the reason this works is because it's looking at these conditions. For a single byte, it's looking for escape byte, and the last byte is not equal to nothing, which would be the case if it's reading through the payload. If it sees an escape, it's going to look for a double escape character. So escape for the current value and escape for the previous value, which is why we set this value here. And we've printed these helpful, we've included these helpful print messages for whether it's found a single escape or a double escape. All right, so let's run the routine. And as you recall, we're trying to see this kind of a message. All right, so we'll stop the existing program, save it, and run it. Okay, we're going to press the user button, and here we've received the information. So you could see that when it sent the data, it's 7 bytes long, the original message, because it includes these extra escape characters. And then starts byte stuffing the frame with escape characters in front of each of these escape values. And now our buffer is 14 bytes. So 14 bytes is what's going to be read. And I've included this last character byte so that we can see whether its value is none or a payload value. And as you can see, it runs into the first escape and it detects it because the last byte was a payload value. So it drops through, throws that escape away and keeps the 7D. All right. So now it's kept the 7D, we read the 6C, 6C, the 6F, 7C, we see another escape character. It sees that that's an escape character, and it throws it away. But it remembers that it had an escape character. So that when it comes back and reads 7C again, it's done a double escape, and this time it knows to keep the escape character in the code, in the buffer, instead of just dropping away. Now it proceeds with reading the checksum, which is a different value. We see an escape for the end byte, but now it's not reading the payload, so the last char value is none, and so that satisfies this case right here. And we find the end byte, and so we're done. And we print out the buffer, and you can see it's included these escape characters just exactly like what we had in the message. All right, hopefully that explains what's going on with escape characters. Okay, I used my code here to explain framing. In my research, I found Python-based utilities. In this table, I listed them in increasing complexity. The programs at the top were MicroPython code or easily migrated to MicroPython. The bottom two included a means to pack and unpack the payload message to include other common data types like integers and floating variables. So that was useful. But their transports assume the microcontroller to be an Arduino. So you're going to have to migrate that code in order to use it with a MicroPython to Python solution. In this video, we learned to build frames, byte stuff it, and send it, whereupon the destination uses a finite state machine to parse the incoming bytes. In summary, framing our message provides a managed approach to sending and receiving messages across serial connections. Using checksum helps destination system ensure it receives the data error-free. Otherwise, it simply rejects the data. For noisier environments, a larger checksum like CRC16 or CRC32 can be used. I like this rigorous method of exchanging data. In the next video, we will look at the desktop code. Thank you.